Hello, IB. We're looking at 13E, which is now the shortest distance from a line to a point. So when we are talking about maybe anything with linear motion, so maybe a boat that's traveling in a linear direction that passes a stationary point, so it could be a buoy, it could be a port, it could be whatever. We want to know when is it that they're actually at the closest distance to one another. So a couple common bits of vocabulary and notation for this section. You've got a ship traveling in a straight line, so it's pretty much what we're talking about here. R is going to be at just any other point on the line that we happen to say is closest to the point P. So point P is our stationary point. And then you have something that's moving past point P. You've got this other point, so A is our initial point, wherever it starts. And then you've got R, which is going to be any other point that's on this line. So we're going to put R as the closest point to P, which is where a perpendicular line is formed. Okay, so we drop a perpendicular line from the stationary object to your traveling object, and we're going to call that point R. So remember, when we talk about linear motion, you usually have this little vector, r, which is the resultant vector, is equal to your initial position plus, for every unit of time, some velocity vector that takes us in a certain direction. Well, we're now going to call point R the foot of the perpendicular from point P to your line. So remember a few sections ago in last chapter when we were talking about the shortest distance. Well, shortest distance here is a perpendicular, and when we were talking about a perpendicular, the dot product happens to be 0 because we're looking for that 90-degree angle. So we now want our dot product from P to R, so we want the vector PR dotted with AR, but really remember AR is a line, but for these two to be perpendicular, it doesn't have to be perpendicular AR, it can be anything with that same velocity vector attached to it. So if we think of B as our velocity vector or our direction, all we need to know is that it's going to be perpendicular to whatever this direction is. So we are going to dot it with the vector B and set it equal to 0. Okay, so we don't have to use the whole equation of that line. We can just use the velocity vector, and then that will give us what our distance is. It'll really give us the position where that closest distance occurs. So we have a couple extra steps in there that we'll go through together in a moment. But the idea for this section is that if you dot that perpendicular drop from the stationary point to your line, and we call that point your foot, so your foot is where that R position is located. If we dot those two, then we wind up with 0, and that'll help us figure out what time that occurs. So our first example is a line has a vector equation of this for any time that's a real number. Let P be the point 5, -1. Find exactly the shortest distance from P to the line. So already we've got this direction occurring. So we start at 1, 2. We're moving in the direction 3, -1. So actually, all right, that looks more realistic now. So 3, -1. And then we've got this point P that's at 5, -1. So if that's at 1, 2, 5, -1, I don't know, down here somewhere. Okay, and we want to drop a perpendicular from this point P to the line so that makes a right angle, and we're going to call that point R. Okay, so find exactly the shortest distance from point P to the line. All right, so our first job is I want to find PR, because what I'm going to want to do is dot PR with this vector that we'll call B, just because that's what we were using in our last example. And we want to make that 0. Okay, so for us, we are going to use, so PR takes us from point P to point R, and R is just any point on this line. So that means R is going to have the position of 1 plus 3t, and 2 minus t, because it's going to be some position on this line. We just don't know exactly where it is. So to get from p to r, we do r minus p. So first thing we need to do is find pr. So that is going to be 1 plus 3t minus 5 and 2 minus t minus negative 1. So PR vector is going to be 1 minus 5, so that's negative 4 plus 3t and 3 minus t. Okay, so now that we have PR, we can dot PR with the actual direction vector. So for S, we'll take PR, there we go, dotted with our velocity vector, make it equal to 0. So we'll wind up with negative 4 plus 3t, 3 minus t, dotted with, and we really only care again about the velocity vector, so that's 3, negative 1. So we want to know what direction this line is going in. We want to force it equal to 0. So remember, our dot product is negative 4 plus 3t times 3. And then we'll add that to negative 1 multiplied by 3 minus t, and we'll set that equal to 0. So we'll wind up with negative 12 plus 9t and negative 3 plus t. So negative 15 plus 10t is equal to 0. And 10t equals 15. So t is going to be 1.5. And we are talking about, we do not know here. So our time is 1.5, some kind of units, we're not sure. All right, but it doesn't ask for the time that it occurs, it wants the actual distance. So what we are now going to do is, because we need the distance from P to R, that's a magnitude of PR. So we'll need to sub in our time into PR so that we can then find the magnitude. So PR at 1.5, when t equals 1.5. All right, is going to be negative 4 plus 3 times 1.5 and 3 minus 1.5. All right, so vector PR when time is 1.5 is 0.5 and 1.5. So now the magnitude of PR is going to be the square root of 0.5 squared plus 1.5 squared. All right, so we wind up with is approximately 1.58 units. And again, we're not sure what the distance units are, but that actually gives us our distance because we took the magnitude of that vector PR. So there are multiple steps here because when you do the dot product, you only find the time when the stationary point and the moving object are closest. So to actually find the distance, we then need to take the magnitude. So read the question very carefully because they will ask you for different pieces. They either want the time that they're the closest or the actual distance that they're going to be the closest. All right, so this number 2 in this section is going to be the last one we'll do for this video. Part of it we'll do together and part we'll leave for you to try on your own. But just reading the question through once, you have an ocean liner that's at 6, -6. It's cruising at a certain speed and given a certain direction. So remember, this is not your velocity vector automatically because you're given a certain speed to be moving at. So we're going to have to do a little work to find our velocity vector. This is only the direction. Then you also have a fishing boat that's anchored at 0, 0. So that would be kind of like our point that's given to us. And this is our moving object, the cruise liner, the ocean liner. And our distance is in kilometer. It looks like our time is in hours. Okay, so we know a little bit already about it. Find in terms of I and J, so in component vector form, unit vector form. the initial position vector of the liner from the fishing boat. All right, we can do that. Write an expression for the moving cruise liner as it's passing the fishing boat at any time. Sure, we can do that too. When will the liner be due east? So in other words, when being what time will it be due east? So again, you're looking for the x-intercept for the fishing boat. And then it says find the time and the position when the liner is nearest the fishing boat. So this is asking for both the time and position, where that last example was asking for the distance. So in this question, we won't actually have to find the distance. We just need to know the time and then what the position is of the liner. All right, so just make sure we're reading these very carefully. So we'll start off, again, just kind of visualizing what's going on here. I have an ocean liner that's at 6, -6. So here's my, we'll call that L for the liner, 6, -6. We've got O, which is where the fishing boat is sitting at 0, 0. Call that O. And it's moving at -3, 4, so it's moving up this direction. All right, so that's all we know so far. So again, find in terms of I and J the initial position vector of the liner from the fishing boat. So if we're looking at the position of the liner here, L, from the fishing boat, we're actually looking at OL as our position vector. And it's just sitting at 6, -6. So 6I and -6J. Because all it's asking for is the position of it. All right, so no motion involved yet. So that would satisfy part A. Part B says write an expression for the position vector of the liner at any time t hours after it has sailed from 6, -6. So now we're actually looking for the linear motion. So again, usually we'll use R for the resultant vector. It starts at 6, -6, and then for every unit of time, it's moving in the direction of -3, 4. The only issue is I can't just put -3, 4 here because we're also given a speed. So this isn't the exact velocity vector yet. So before I leave that, or cross that out, I actually need to figure out, in order for me to have a speed of 10 units, kilometers per hour, that means that that needs to be the square root of -3 and 4 squared. So that'd be 9 and 16, which is not going to work. So that means it must be parallel. So it must be another vector that's parallel to it. So magnitude 10 will be k times this, which is 25. So that would be 10 equals k times 5. So k is 2. So remember, we can have, these can be equal, for them to be parallel, they're equal by a scalar, and my scalar is 2. So in other words, this direction vector here has to be multiplied by 2. So this is actually going to be 2 times -3 and 4. So my position vector, I'll actually go from 6, -6 plus t, and that will be -6 and 8, okay? Because that takes into account the speed I'm moving at and the direction that I'm moving in. So those two together give me the velocity vector of -6 and 8. So write an expression for the position vector of the liner at any time t after it has sailed. So here's my expression for the position vector of the liner. When will the liner be due east of the fishing boat? So again, we talked about that one. Due east would just be our x-intercept. So we'll set your y component equal to 0. So we'll get 8t equals 6, and t equals 6/8 or 3/4. And since we're talking about hours, that would be about 45 minutes. So 3/4 of an hour. And then last but not least, part D says find the time and the position of the liner when it's nearest to the fishing boat. So what I'm going to do is I'm going to zoom in on this situation here. And we've got the liner moving in this direction. We have 0, 0. We're going to drop our foot to the liner in order to make our perpendicular. So again, we'll call this our position R. This will be our initial point P, or O in this case. 0, 0. Okay, and we want PR dotted with our velocity vector, which for this one is going to be negative 6, 8. You could also use negative 3, 4. That should be fine as well, because it's parallel to it, and we want to set these equal to 0. So the first thing we need to do is find PR. So we're going from 0, 0, so that makes it a little bit easier. R is just the position, so 6 and negative 6 t, and negative 6 plus 8t. All right, so minus 0, 0, so that'll just be 6 minus 6t, negative 6 plus 8t, dotted with our direction, so negative 6 and 8. Remember, you can use negative 6 and 8, or you can use negative 3, 4, just because they're going to be parallel to each other, so they'll still wind up being perpendicular to the PR vector. And then we wind up dotting these, so 6, negative 6 times 6 minus 6t plus 8 times negative 6 plus 8t equals 0. So what we wind up with here is that your t is equal to 0.84 hours. So that is our time. But then because part D also says find the position, we will also need to sub in 0.84 to find the position, and that's going to be of our the point R on that linear motion of the liner. So at t equals 0.84. So what we'll wind up doing is subbing back in. So we have 6 minus 6 times 0.84. And then we have negative 6 plus 8 times 0.84. All right, so we wind up with 0.96 and 0.72. So if you think back to our picture, 0.96 and 0.72 is very close to 0, 0. So it's pretty much when it's about there. That's when it's the closest. All right, so it does wind up working with our little sketch from earlier. All right, guys, so that satisfies that one. Just to think about how this applies to 3 dimensions, for you guys to try before you head to class tomorrow. Example 12, consider this point, and now you have 3 components. So in 3-dimensional space, think about what you would do, and does it follow the same structure? All right, guys, have a good night. See you tomorrow.